In this video, we will now work through some practice questions, which I have actually taken from the problem set. So the purpose of this video is to show you exactly how to approach answering the questions, the multiple choice questions, which you will be faced with regard to the semantics of our deductive logic. And again, this is what will preoccupy us for this week and next week when we conclude our unit on deductive logic. So here is an example question. We're given the sentence A and B, or B and A. And then we're asked, is this sentence a tautology, a contradiction, or a contingent sentence? So in order to answer this question, what we do is we construct the truth table for the sentence. And then once we have constructed it, we look at the column of T's and F's below the main connective, which in this case is the disjunction. And we see whether all of them are T's, and if they are, then it's a tautology. If all of them are F's, it's a contradiction. And if there are a mix of T's and F's, then it's contingent. So let us go ahead and create this truth table. So hopefully my technology works. So the first part of creating a truth table, and I'm going to be following the method which I introduced you in the previous lecture. So the first thing is we list the basic atomic sentences that occur in the sentence, and that is A and B. And then on the right-hand side, we write out the full sentence, which I have just done. Now, and actually I realized I think the first step is actually determining the number of rows, but whether you do that first or after this part doesn't really matter. I mean, according to the specific method I gave in the previous lecture, but in any case, what we have to do is we have to figure out how many rows there will be. And we know how many rows there will be given the number of atomic sentence letters. And here we have 2, so that means that there's going to be 4 rows. There's going to be 4 possible ways of combining different truth values for A and B. And as was mentioned in that lecture, the formula for that is to the power of n, where n is the number of atomic sentence letters. So here, because n is 2, we have 4 rows. And then we fill in, the way we fill in these 4 rows in order to make sure that we capture all the possible ways of assigning different truth values is we start on the right-hand side and we alternate for each of the 4 rows between true and false. And then we move over to the left. And then we do 2 truths and 2 false. So here, by following that technique, we have now listed out all the possible valuations, all the possible ways of assigning truth values, the true and the false, to these atomic sentences. We have the first where they're both true, the second where A is true and B is false, the third where A is false and B is true, and the final one where they're both false. Now, the rest of our task is we have to fill in the truth values throughout the right-hand side. And what we do is we copy the assignment of the truth values to the atomic sentences, which we have in each row. And then once we've done that, we use our knowledge of the meaning of the connectives to determine the rest. So we're going to work row by row. the first thing we do is we go through and we copy the truth values we have here for each of the connectives to their occurrences. And then we see how they determine the rest. So conjunction is true when both of the conjuncts are true, which works. And disjunction requires at least one, and here we have both, which is at least one. So we have the entire sentence is true on this row. Now we move to the next row. And because B is false, that means these conjunctions are false. And here we have that it's not the case that at least one of the conjuncts is true. So we have is false. Now I want to really emphasize something, which I think I already mentioned, which is that when you're figuring out whether a connective has a true or false below it on a row, it's very important that you are comparing the right other columns. So this disjunction here is between A and B on the one hand and B and A on the other. So the two disjuncts of this disjunction are A and B, B and A. So what that means is that when you're determining whether at least one of the disjuncts is true, it's crucial that you're comparing this column here to this column here, because this column represents the truth value of the entire conjunction, this as well as this one. So the reason why the disjunction is false here is because on this row, this entire conjunction is false, and this entire conjunction is false. And that's why we put false here. So these arrows are representing that when I'm filling in this column, I'm looking at what's under this conjunction and this conjunction. So I'll quickly do the rest, which should be simple. So here we have that A is false, so that's going to make both these conjunctions false again. And then again, we'll have false, because we have two false for the disjuncts. And then in this final row, all of the atomic sentences are false. And so the conjunctions will be false again, and then also the entire disjunction will be false. So now that we have constructed the truth table, we then look at the column under the main connective, and we look at the distribution of truth values. And here we see that there's one case in which is true, and there's at least one case in which is false. And that means that this sentence is contingent, because there's at least one row on which is true, and there's at least one row on which is false. So it's possible for this sentence to be true, and it's possible for it to be false. And that's how we we determined the answer to our question, which we began with. So let me switch back. So we determined that the sentence is a contingent sentence. And that's exactly how to go about answering any question like this. You construct the truth table for the sentence, and then you look at the column under the main connective and see whether it's all T's, it's all F's, or it's a mix of. Now we move to the next practice question. Here we're not wondering whether a single sentence has the property of being a logical truth or falsehood or contingency, but here we're wondering about whether pairs of sentences are equivalent or not. So here we're given in the question a sentence A or B or C, and we're asked which of the following sentences it is equivalent to. Now, in some case, in general, a given sentence is equivalent to many, many other sentences. So in a given question, there might be multiple correct answers. In this question, however, I think only one of these three is a correct answer. That is, I think only one of these three is equivalent to the given sentence A or B or C. So now to determine which one is the correct answer, we have to construct truth tables comparing the given sentence with each of these. And when we construct each of those truth tables, we can look at the column under the main connective. So here's this V disjunction. And for instance, the main connective here, or here, or here, and we see whether they have exactly the same distribution of truth values or not. And if they don't, if there's some row in which under here is a T, say, and under here is an F, or vice versa, we know that they're not equivalent. But if when we're comparing this sentence and one of these other ones, if we see that they're exactly true and false on the same rows, then we know that they're equivalent. So let us build our first truth table comparing this sentence with this sentence. So the first thing we note is that there are 3 atomic sentences this time. There is A, there is B, and C. And now, so we list the 3 atomic sentences on the left-hand column, and then we write out the sentence in the next one. So I need to be reminded actually of what the sentence is. Okay, so A or B or C. A or B or C. Please pardon my messy writing. Okay, and then if I remember that what we're interested in is A or B. So now that we have the table set up, we now have to fill it in with all the possible rows which correspond to all the possible combinations of truth values for these 3 sentences. Now the cases we've seen so far, we only have 2, and in that case we had 4 rows. But now when we have 3 atomic sentences, we have 8 rows. So again, our general formula was that 2 to the power of n is the number of rows, where n is the number of atomic sentences. So here we have 8 rows. And so we know we have 8 rows, but the way we fill in those 8 rows is the exact same procedure that we did in the case of 2 letters. So what we do is we start with the rightmost sentence letter, and we go down the rows alternating between true and false 8 times. So I think that's 8. Yeah. So here we've done 8 rows where we alternate true and false back and forth. Then we move 1 to the left, and we alternate a bit less rapidly. So here we do 2 truth, and then 2 falses, 2 true, and 2 falses. And then we move 1 more to the left to A, and here we do 4 truth and 4 false. And now, following this method, we've now listed out all the possible combinations of truth values for these 3 basic sentence letters. Now, the rest of our task is just about filling in what the overall truth values is given our knowledge of how these connectives work. So I'm going to do this quickly, and I'm not going to walk through all my reasoning for the sake of time, but hopefully as I'm filling this in, you can see why I'm doing what I'm doing. Okay, so I'm stopping here at the 7th row, and even though I have one more row to go, I have an answer to the question of whether these two sentences are equivalent or not. Because here on this row, the 7th row here, I have found a case where the sentence A or B or C is true, and the sentence A or B is false. That means that I have found a case where these two sentences have a different overall truth value. And that means that they're not equivalent. So to put that in another way, what it means for these two sentences to be equivalent is for the first to entail the second and vice versa. That is, A or B or C entails A or B, and A or B entails A or B or C. And what that means is that whenever A or B or C is true, A or B also has to be true. Because that's what it means for A or B or C to entail A or B. However, what we see is that in this case, in this assignment of truth values to the three atomic sentences, is possible. In this case, we have that A or B or C is true, but A or B is not. That means that A or B or C does not entail A or B, which means that they are not equivalent. So we know from this row that these two sentences are not equivalent. So we know that this sentence here is not equivalent with this sentence, so this is A or B is not the correct answer. So now let's look at the second one. A or B or C. So let me try to do this a bit quickly. So I'll get rid of this circle here, but we will have to erase this. So here we're looking at A or B or C. So here we have in the second main column the new formula. And now we're going to go through and construct and fill out the truth values which we know from the assignments of the valuations here and our knowledge of how the connective disjunction works, and we're going to fill it all out. Okay, so here again I won't talk through my reasoning for the sake of time. Oops. Okay, so we've just completed the entire truth table. And what we see is that when we look at all of the rows under the main connective of each of these sentences, we see that in every row they have the same truth value. So they're all, so in this first 7 rows, this entire sentence is true, A or B or C, and also the sentence A or B or C is true. And in the final 8th row, we see that this first sentence is false and the second sentence is false. So we see that in their overall truth table, both these sentences have the same distribution of truth values in every row under their main connective. And that's exactly what it means to say that they are logically equivalent. So by constructing the truth table that we just did, we determined that the sentence A or B or C is logically equivalent to A or B or C. Now I'm not going to, for the sake of time, I'm not going to work through this last one, but if you constructed this truth table comparing our given sentence to A and B or C, you would find that there is at least one row on which they differ in truth value and therefore that they are not equivalent. So now let's go to our final practice question. So here we are. So this final practice question is about validity or entailment. So we saw when the first set had to do with whether a given sentence was a tautology, a contradiction, or a contingent. We saw one that was asking about the equivalence of various sentences. And now finally we're asking about entailment. So for this questions of this final type, what we're given is we're given premises of an argument. So we are to imagine an argument with A as its first premise and B as its second premise. And then we're going to have to determine which of these given sentences here, if they were the conclusion of that argument, would make a valid argument. So I'm going to walk through with the first one how to create a truth table to test whether the argument with premise 1A, premise 2B, and conclusion A and B to check whether or not that is valid. So we have to go back. Now let's erase. So here we have, on the left-hand side, we have our two atomic sentences that are featured, A and B. Then we're going to have a big column for each premise. And here it's very simple, so we just have the first premise is A, second premise is B. And then we have we just add another main column for the conclusion. And now we're going to quickly fill in all the possible combinations for A and B. So here, because there's only two, there's only 4 possible combinations. And this is very similar to what we have done already, which is that we're going to fill in the rest of these values according to what each row says about the basic sentence letters. And then we're going to look and we're going to figure out whether there's any row on which all of the premises have true under them and the conclusion has false. And if there is such a row, we know it's not a valid argument. We know it's therefore possible for the conclusion, for the premises to be true and the conclusion false. But if we see that on every row in which the premises are true, the conclusion is also true, we will see that it is a valid argument. So let us fill this in. And again, the premises are very simple. They're just the letters themselves. Oops, I made a mistake here. So again, with conjunction, the entire conjunction is true just in case both conjuncts are true. So in this first row, both conjuncts are true, so it's true. But in all the other rows, it's not the case that both conjuncts are true. So now we've very quickly completed the truth table for the argument. And now we ask ourselves, in every row in which both or all of the premises, in this case there's 2 premises, so in every row in which all of the premises are true, is the conclusion also true? So as it happens, there is only one row in which both the premises are true, which is the top one. And in this top one, we see that the conclusion is also true. So that's how we know that the argument with the premises A, and then the premise one is A and premise two is B, to the conclusion A and B is a valid argument, because whenever both the premises are true, the conclusion is also true. So we see that there's many other rows, there's many other possible ways things might be in which the conclusion is false. So B could be false, and therefore the conjunction might be false. However, in the case where B is false, the premise B is false, so it's not the case that all the premises are true. So what matters for validity or entailment is that whenever all of the premises are true, the conclusion is also true. And it's fine for there to be possible cases in which the conclusion is false, but those have to be cases in which at least one of the premises is false itself. So here we see in every row in which all the premises are true, and that's just the first row, the conclusion is also true. And that's how we know that the argument from premises A and B to the conclusion A and B is valid. And now what you can do is you can construct similar truth tables where you plug in, instead of A and B as a conclusion, you plug in these formula. And then you can wonder, and you can look and determine whether these work as valid conclusions to the argument. So that concludes, for now, how we can use truth tables to test for the rigorous semantic notions that I have just introduced in this lecture.